Hello everyone, my name is Mario Barbara from the Department of Computer Science, University of Haifa, the author of the paper Prompts-to-Summaries, Zero-Shot Language Guided Video Summarization. Video summarization aims to generate a short version of a video by picking the most important shots containing the main content of the original video. Current video summarization approaches face two major drawbacks. First, most solutions, whether supervised or unsupervised, depend heavily on the training data, limiting their ability to generalize beyond the distribution they were trained on, and thus reducing their real-world applicability. Second, they are constrained to generate predefined video summarization tasks and can't accommodate user-specified text queries to guide the summarization process towards specific content or themes. Motivated by the previous discussion, we introduce our approach. Given an input video, our method generates a personalized video summary by computing frame-level importance scores conditioned on user-provided query. The pipeline consists of scene detection, scene boundary refinement using image embeddings, and text-to-scene description generated using video language model. Then, a large language model evaluates the relevance of each scene description with respect to the user query and the full video context. And using temporal smoothing and heuristic function, we convert them into frame-level importance scores, which guide the final query summarization. All that without requiring any training data. Method: first phase scene detection. The goal is to segment a video into meaningful, non-overlapping scenes that each represent a distinct event or action. Step 1. Initial scene detection. We detect scene boundaries by computing the mean intensity difference between consecutive frames. A threshold is used to decide when the difference is large enough to mark a new scene. Instead of using a fixed threshold, we dynamically select it. We evaluate a range of predefined threshold values and select a threshold that maximizes the negative rate of change in the number of scenes with respect to the threshold to balance over-segmentation and under-segmentation. Step 2. Scene boundary refinement. To improve coherence and semantic consistency, we refine the initial scene segmentation by merging excessively short scenes. Scene is defined as short if it contains fewer than m frames. We extract embeddings for each frame using a pre-trained image encoder and compute mean embeddings for each scene. Short scenes and then merge with their most similar neighboring scene based on the embeddings cosine similarity. Phase 2. Description generation. The goal is to generate a textual description for each scene and for the full video. We use a pre-trained video language model that was trained on large-scale video datasets involving video Q&A and visual language tasks. Phase 3. Scene score prediction. The goal is to assign an importance score to each scene based on its textual description. For each scene, we craft a prompt that includes the scene description and the full video description, and the large language model acts as a judge, assigning a score from 1 to 100 for each scene, where 1 means that the scene is irrelevant and 100 means that the scene is crucial to be included in the summary. This allows a zero-shot semantically guided evaluation for each scene's relevance. The fourth and final phase, frame-level score prediction. The goal is to produce a fine-grained importance score for each frame to generate a compact summary. This phase has 3 steps. First, initial frame scores. Scene scores are normalized to emphasize relative difference in importance. Then, each frame inherits its scene score. And finally, to avoid abrupt transition between scenes, we apply temporal smoothing using a cosine-based function, blending score across scenes. This transition helps eliminate unnatural jumps in score values, resulting in more coherent and gradual shift across scene boundaries. Step 2. Frame weighting. We divide each scene into fixed size segments of size W. For each segment, we compute the consistency and uniqueness, where consistency is computed as the proportion of the frames from the dominant cluster based on the frame labels, and uniqueness is the standard deviation from the segment's embedding. A final frame weight is calculated using a weighted sum of the consistency and uniqueness, governed by the parameter sigma. And finally, Step 3. Fusion. The final frame score is obtained by multiplying the smoothed initial score with the frame's weight. Frame scores and then normalized within each scene to ensure fair distribution and prevent scene bias. Evaluation and results. To evaluate our method on the standard video summarization task, we tested our pipeline on SUMME and TV-SUM datasets. In this table, we can see that although our approach performs competitively with the supervised approaches, our primary focus is to compare with the unsupervised ones. The results demonstrate that our unsupervised zero-shot pipeline surpasses all competitive unsupervised methods. Specifically, our approach achieves a 2.7% improvement in SUMME dataset and a 0.2 improvement in TV-SUM dataset compared to the current state-of-the-art unsupervised method. We also tested our pipeline in QFVS dataset, where we guide the summarization process using a user query. As shown, our training-free zero-shot approach always outperforms the 4 classical supervised baselines. And using the same settings used in the current state-of-the-art clipped model, our zero-shot pipeline reaches an F1 score of 53.4, virtually matching the 54.4 achieved by the fully supervised clipped model. A pair video analysis further underlines our robustness. We surpass the current state-of-the-art by more than 2 precision points on video 2 and equal its performance in the notoriously challenging video 4. And finally, fine-grained video summarization. Here we introduce our dataset VidSumReason, our new benchmark for fine-grained reasoning-driven video summarization from natural language queries. It contains 9 videos, 2 to 6 minutes in duration, each video paired with 1 to 3 queries, totaling 20 video query pairs. Unlike UFVS dataset, where queries which merely refer to obvious visual entities, such as focusing on car, tree, or sky, VidSumReason possesses a richer, more nuanced prompt that tests interpretation, temporal reasoning, and the use of general knowledge. Our dataset queries not only prioritize certain content, but also serves as a filter to exclude scenes, for example, filtering violence or excluding PG-13+ material. VidSumReason has 4 query classes: standard with special attribute, reasoning, and reasoning with general knowledge. We also conducted a quantitative comparison against a random baseline. We report the total F1 score and the F1 score across the 4 different query classes. As we can see, the performance gap is prominent in every query class, such as reasoning, where understanding of temporal dependencies is required. To further illustrate the alignment between our pipeline predictions and the user intent, we included the following visualization. The top plot displays the ground truth importance scores in blue along with the ground truth summary in red, while the bottom plot overlays the predicted summary with green boxes on the same importance scores. Frames that appear in both summaries and align with the user's query, highlighted in green, and frames that correspond to a key event in the video and also shared between the two summaries are highlighted in black. This overlap indicates that the model not only captures query-specific segments, but also preserves key content from the original video. And of course, additional details and experimental studies to validate our design choices are provided in the paper. Thank you for listening.